This table here kind of summarizes some of the stuff I was doing earlier, right? Ideal, 741, LF157. The only thing on here that I didn't really cover is the common mode rejection ratio. Again, ideally, infinite. Reality, for the 741, about 90 dB. For the 157, about 100 dB. Just a few other numbers. Now, some of the other aspects of my op amp that I need to talk about, some of them are summarized in a few diagrams that are on or in the text, and I've got them up here, and then I'll throw a little other stuff on the side over here when I'm ready for that. All right, so this, of course, shows the frequency response of typical 741. So 10 hertz right there. This does show 100 where it starts to come down. This, though, is for the common mode rejection ratio, all right, specifically. The other graphs are coming, right? So your common mode rejection ratio is about 90 dB, right? And it starts to drop off. You've got your maximum peak to peak. Now, what does this have to do with? Well, this is because of that output resistance. And so this assumes that I'm powering the op amp with plus and minus 15 volts. So theoretically, that gives you a 30 volt peak to peak. The thing is, in the design of the circuit, there are limits to how far it can go. And so with a lot of load resistance and therefore not much voltage drop across the internal resistance, I can get up to about 27 volts peak to peak with plus or minus 15 volts power. And as that load resistance drops, and notice this is a nonlinear scale here, right? This is a from 10 to 1 to 0.1, right? It's a log scale. So this is linear, so don't worry about the graph too much. But we can see that we still can get quite a bit of output voltage, even down to a few hundred ohms of resistance. But when it gets too low, I just can't get any more out. Now, this is based, or this is a result of that internal output resistance. There's another factor that we're going to talk about as well that can affect that maximum peak to peak. We'll get to that here in a second. There's your voltage gain, right? So this, of course, shows my cutoff frequency at 10 hertz, right? With 100,000, 100 dB, 0.707, of course. Yeah, so unity gain frequency, boom, right there, 1 meg. Now, this looks like our ideal, or actually looks like a real Bode plot because of the curvature here. But notice that this is, of course, a log scale. Instead of decibels, this is also a log scale, which when you have linear decibels, that's the same as a log. So that's why the shape is the same. All right. Now, power bandwidth, right? So this is where I'm going to have to do a little aside here. So one of the things that happens, with having an upper cutoff frequency. You actually did this for experiment 37. You put in a square wave. To an amplifier that has an upper cutoff frequency, what happens? It's like a charging capacitor. It's essentially what you have. And of course, when you found your upper cutoff frequency, you're like, oh yeah, well, there's 100%. So we'll find 90, we'll find 10, and that's your rise time. Okay? That's what happens if I put a square wave in. But what that also means is there is a maximum rate at which the output voltage can change. That maximum rate happens right there at the initial change. So the slope of that curve is what is known as the slew rate. Essentially, it's that capacitor charging up, right? The capacitor that's in parallel creating that upper cutoff frequency has to charge up. That's what creates it. So what effect does that have? Well, when I have a sinusoidal waveform, the maximum slope occurs right there. I went through some of the math for this back when I think I was deriving the reactance formula for capacitors and inductors. The slope of this line is basically going to be the derivative of the sinusoidal function, which is the peak voltage times the sine of 2 pi frequency times time. That's this waveform. So if I take the derivative of this with respect to time, that gives me the slope. And when you do that, you basically get 2 pi frequency times the peak voltage times the cosine function. Chain rule, all that. That's my slope. Let me rephrase that. That's my, no, that is right. That is my slope. The maximum slope is when the cosine is at a maximum, which is 1. So there's your maximum slope. Well, the slew rate limits how fast this can respond. And so that maximum slope is limited by the slew rate. So what that means is if I take and set the slew rate equal to that maximum slope, 2 pi frequency times the peak voltage, and I solve for the frequency, right? This is going to be the maximum frequency based on this slew rate. Because remember, the higher the frequency, the higher that slope. But that slope is also affected by the peak voltage. Well, that's in the formula too. So what I can do is I can solve for that maximum frequency by taking the slew rate divided by 2 pi times the peak voltage. So this creates what that graph is basically talking about, which is the power bandwidth. This is something beyond the upper cutoff frequency. This is something beyond even that. So the higher the peak voltage for a given slew rate, the lower that maximum frequency. Because if the output of the op amp cannot keep up with the output signal it's trying to drive, what's going to happen? Let's say my slew rate, the maximum rate of change I can get is this. Well, it's going to be going up as fast as it can, trying to keep up, trying to keep up, trying to keep up. Oh, now it's going down. Trying to keep up, trying to keep up, trying to keep up, trying to keep up. Now it's going down, up again. What you end up doing is you end up turning the output signal from the sinusoidal shape that you want, in worst case, all the way to a triangle. Before you get to the triangle shape, what you do is you start to distort the sine wave. Maybe 80, it's like trying to keep up. Can't quite, higher slew rate is keeping up until it gets to there. And then it's kind of keeping up until it can't quite keep up anymore. The slew rate kind of goes both ways. So now you get a distortion. So even before you get to the triangle, it starts to distort. But the triangle is the extreme. So that's what this graph is showing us here. And by the way, the slew rate for the 741 typical value, about 1/2 volt per microsecond. So the power bandwidth, so we've already talked about the concept of the upper cutoff frequency. That is, of course, just the gain of the amplifier. Power bandwidth is not just about frequency, it's also about the peak voltage you're trying to get out. So depending on what you are trying to do, what the gain of the amplifier is, what the input is, you may have an upper limit to the output from the op amp if you try and make it too big. So maybe if you're only trying to get 1 volt peak to peak, all right, you're good all the way up to 80 kilohertz. Well, that is probably way above the gain that you may have, right? So, and we'll see that here in a second. But if I have a gain, say, of 10, that actually makes my upper cutoff frequency 100 kilohertz or so, roughly. So with only 1 volt, I'm limited to 80. But hey, if I try and get 4 volts peak to peak out, now I'm down to 20 kilohertz. That's what that formula gives me. Any questions on that? Here's some other op amps. Remember I said earlier, a lot of different op amps out here, right? What am I looking for? Do I want a really high slew rate? I've got one right here, LM7171, 4,100 volts per microsecond. By the way, the slew rate is also associated with, typically, the unity gain frequency, right? 200 megahertz. Pretty high. There's your high frequency one there. All right. What if, and I also have, there's a couple other things on here that weren't on before. All right. For example, where is it? Oh, there it is. Maximum output current for a 741, about 25 milliamps. What if I want more? All righty. Oh, here, I got this. The LM675, 3 amps. That's a lot more. Okay. So you can kind of go through here and figure out what you're looking for, right? What do I want? Do I want a good high slew rate because maybe I'm putting in some type of square wave and I want a good fast response? Do I want a really high common mode rejection ratio? There's one for you. Right? 110 dB. Do I need a really low input bias current, right? Then get down to the microamps down here. Oh, that's pretty high, actually. This is nanoamps. So I guess they don't have the LM. Yeah, they don't have the LM159 on here. That was the one that was in picoamps. All right. But you got all the different stuff you can look for. All right. Any questions on all this? Good. All right. Now, what can we do with our op amp? I'm going to go through 3 quick circuits here. The analysis that we're going to do on them is not going to be real heavy. All right, we'll get more into it in future. For the first one, and I'm going to go through this fairly quickly here because, again, some of you have seen this already. There are going to be 2 assumptions that we're going to make about our op amp. two big assumptions. First assumption, because of the very high input resistance of the op amp, we're going to assume current into the op amp zero. This is for 741, typically 2 mega ohms. And these resistors are kilo ohms. We are talking over a factor of 100 difference between the current that I'm working with and any current that might be going into the op amp. So we ignore it. Secondly, this one's a little bit trickier, but again, most of you have seen this before. Sorry, Ben. Okay. With negative feedback. Now, in general, what does negative feedback do to the gain of an amplifier? Makes it go down. Open loop voltage gain of my op amp is 100,000. That's huge, right? That is the actual voltage gain between V1 and V2. So if the output voltage of my op amp is equal to 100,000 times V1 minus V2, as measured here and there. With negative feedback, voltage gain is reduced. Now, the voltage gain of the op amp is not reduced. It is the voltage gain of the circuit that is reduced. And so by reducing that voltage gain, I can be assured that my output voltage here will be somewhat limited, or I will control it. I will have a maximum, however you want to look at it. So let's just say that that output is 10 volts, right? If I'm powering this op amp with plus or minus 12 volts, I can pretty easily get up to 10 volts. And if I'm limiting myself to that 10 volts divided by 100,000 will be V1 minus V2. If you do that math, that comes out to 100 microvolts, or 1/10 of the millivolt. That's about as low as you can read with our meters. And that's if you go to the 300 millivolt scale. Only then can you get down to a 10th of a millivolt. Otherwise, it might as well be 1. Okay? And so if we just say, all right, that's about 0, that means that when I have negative feedback, V1 and V2 will be assumed to be equal. Those two assumptions allow me to make some very simple circuits here that do some pretty powerful work. For example, this circuit right here. With these two assumptions, because V1 is connected to ground, the voltage is 0. That also means that the voltage V2 is also 0. That creates what is known as a virtual ground. Now, I say virtual because it's not actually connected to ground. There is no path for current flow, but it will act like ground. So that means that my Vn coming in here, and I do have this as a sinusoidal signal. It could be DC, whatever it is, but I always have a reference. So if I assume that's my reference, that's going to create a current Vn divided by R1. That current, because all that voltage, this is with Vn with respect to ground, And because R1, this side of it is virtually connected to ground, all that voltage is across R1, and that is my current. Second assumption, or technically is our first assumption, all that current does not flow into the op amp. None of it does, right? Input current 0. That's a virtual ground, no path, which means all of that current flows through RF. Note the direction of the current. Creates this voltage drop. Now, the output voltage here, with respect to a ground, oh look, there's a ground, is simply the voltage across the feedback resistor. Technically, negative, right? Because it's negative with respect to ground. Well, voltage across a resistor will simply be equal to current times that resistance. That current is Vn divided by R1 times the feedback resistor. So that means the output voltage of this circuit will be equal to negative RF over R1 times Vn, or the voltage gain of the circuit will be negative RF divided by R1. So what does the negative mean? Inverted, okay? This is an inverting amplifier. Inverting amplifier.
Out to AC voltage there.
AC or DC, no lower cutoff frequency, it doesn't matter. I put in a positive voltage, I'll get a negative voltage out. I put in a sine wave, I'll get a sine wave out. Inverted, 180 degrees out of phase. And note what the voltage gain is. And by the way, I'm going to clarify this here. This is my closed loop voltage gain, right? By using the negative feedback, I'm limiting the gain with a closed loop feedback. I haven't changed the gain of the op amp, only the response of the circuit. And that voltage gain is set by two physical resistors that you put in. No more R prime E to deal with, right? Very linear response because they're resistors, they don't change. So you're not going to have any distortion from too high of a gain, all right, or too high of a signal, other than what we've already talked about. There's a power bandwidth that we have to calculate. Yes?
How that closed loop, that's without feedback.
No, that's open loop. Open loop is no
Yeah.
feedback. Still throw the word loop in there just to confuse you, right? Now, a few other factors, right? When we look at amplifiers, there's lots of things we like to look at, all right? The input impedance, closed loop. Well, essentially, what is the input voltage divided by the input current? Well, it is simply equal to R1. So by the selection of R1, you are selecting the input impedance of this circuit. Now, bandwidth. Let's talk about the response of this circuit. We know that the 741 op amp, I had this drawn up earlier, but we'll go ahead and put this on there. I'm going to do the same thing that one did here, right? For the op amp, this is 1 megahertz. 20 dB per decade. All right, even though I don't have decades over here, I'm drawing it as a decade. I'm sorry, that's over here. Even though I have 20 dB, each time I change by a factor of 10, that is 20 dB. Now, if I were to design this circuit to have a voltage gain of, say, about 10, what I'm essentially doing, oh, by the way, this is, of course, at 10 hertz. By making the voltage gain overall of my circuit 10, I'm changing the response of that circuit to this. Now, he does modify it a little bit, right? The way I have this here, this upper cutoff frequency would be 100 kilohertz, right? 1 decade below, 20 dB above. So the actual formula that he provides us is that the closed loop upper cutoff frequency will basically be the unity gain frequency divided by the voltage gain closed loop plus 1. Now that's 4. Now this is the magnitude of it. So even though the voltage gain itself is negative, it has magnitude. So in my example here, 10, this would actually be 1 million divided by 11, which would be 90.9 kilohertz instead of the 100K that I approximated. Pretty close, not much difference. And the higher your gain is, the less that plus 1 affects things. So I have essentially, even though the op amp itself has an upper cutoff frequency of 10 hertz, that's because of the 100,000 gain. If I reduce the gain of my circuit, the upper cutoff frequency goes up. Now, this is an op amp, all right? And so because this is an op amp, it has my input bias currents, input offset currents, and my input offset voltage. Well, imagine that's only a millivolt, right? We went through some numbers, it could be higher or lower. But with 1 millivolt times a gain of 100,000, boom, I'm going to end up saturated one way or another. But by using negative feedback, the input error to get your output error going to be whatever that input error is times that closed loop voltage gain. So now if I've got an input error that adds up to a few millivolts and my gain is 10, well, now it's only a few tens of millivolts. Another advantage. Now, I do only have resistors on one input. So what would I want for a matching base resistor down here? Keep in mind that we're looking at 2 different paths of current here that does actually allow whatever current goes in there, right? So inside here, we have that, right? Output resistance. This output resistance is relatively small compared to these other resistors. And so if I do a Thevenin and look back this way, this replaces with a short, so I have R1 to ground. I have the feedback resistance through here to ground. And so we approximate an equivalent base resistance. If I want to put a resistor in here to match base resistances, would be the parallel combination of those 2 resistors. We want to match. inverting amp. Questions on it? Mix things up a little bit here. I didn't clarify one thing earlier, right? When I talked about feedback path, how do we know we have negative feedback? If a path exists from the output of the op amp to the inverting input, I have negative feedback. Pretty simple. Notice I'm labeling the resistor RF. Just makes life easy. Feedback. So same assumptions here. Now, here, V2 is not grounded like I had over there. Or no, V1 is grounded. Never mind. Okay. V1 here is the input voltage, which because of negative feedback means that V2 is also equal to the input voltage. Well, V2 is connected across R1. So the input voltage is across R1. I'm using the same reference points, right? Plus, plus, plus. Now, that means that I have current flowing through R1, I'll call it current 1, that is equal to the input voltage divided by R1. I love Ohm's law. Well, where's that current coming from? Well, the only place it can come from is down this way, right? No current in this line here. First assumption. So that means that that current creates a voltage drop across RF. Voltage across RF will be equal to RF times current 1, or RF divided by R1 times Vn. Well, what is the output voltage? With respect to ground, the output voltage is voltage across R1 plus the voltage across RF. The voltage across R1 is the input voltage. Voltage across RF is the input voltage times RF divided by R1. So when I factor out the input voltage, I'm left with 1 plus RF divided by R1 to give me a voltage gain of, by both sides by the input voltage, RF divided by R1 plus 1. No negative sign. This is my non-inverting amplifier. Once again, the actual voltage gain, oh, I forgot my closed loop. See ya. There. Closed loop voltage gain is once again determined by resistors that you put in the circuit. And very similar to our other quantities that we looked at, right? By lowering the voltage gain, I increase the upper cutoff frequency. This time I don't add the 1. It's just the closed loop voltage gain. So you can kind of see where these are similar, right? So the formula for the inverting amplifier is voltage gain plus one. I've already got the plus one there as part of that formula. Where it kind of works out. Now, as my circuit is drawn here, what is the input impedance? It's just the op amp, which is really high. So he doesn't provide a number there. But if we want to put in a matching base resistor, I could put it that way, I could put it in series, whichever way, right? But if I put in my matching base resistor, call that RB2. From the perspective of the other base, again, looking back out, feminizing, R1 to ground, the feedback resistor back through here to ground. And so RB2 would again be R1 parallel with the feedback. Non-inverting amp. Now, I'm going to make two small modifications to both of those circuits. For the first one, I'm going to take my inverting amplifier, with my feedback resistor. But now I'm going to go ahead and add in, I don't know, a few input voltages. Call that V1, I'll call it VA, VB, VC. And we'll go ahead and call this R1, R2, R3. Those of you that had 214 should recognize this. You remember what I call this? No. No?
Say comparator. Didn't it do the arcs?
Let's see what happens. Again, negative feedback exists. Virtual ground, which means this point is 0 volts. So relative to here, I have, we'll call that current 3, current 2, current 1, all of which can be calculated by taking the respective voltage divided by the respective resistor. What happens to those three currents at that point? Kirchhoff says they add up. And so the actual current coming in here is the sum of those currents. And that's the actual current that comes out there. Now, in this direction, we get that same polarity. Those currents are then multiplied by RF. So what you end up with an output voltage will be negative RF times those currents. What is this called? Circuit is a summing amplifier. It's inverting. It does add up. And there's different ways I can write this, right? I could take this and say, well, it's negative, and then distribute RF across here. And so I would have VA times RF divided by R1 plus VB times RF divided by R2 plus RF. I'm sorry, VC times RF divided by R3. I can make each input have a different gain. I can weight things. As in factors of 2 for a digital to analog converter, which is what you all did for lab number 1 in 214, for those of you that took it. Again, Ben, you're off the hook. All right. Lastly, we do a modification of my non-inverting amplifier. Fairly straightforward here. Well, actually, one other thing here, right? No resistor here. If I want to add a matching base resistor, looking back from the other base, I have RF to ground, R1 to ground, R2 to ground, R3 to ground. So basically it would be the parallel combination of all of the resistors used. All right, sorry. What's this circuit? Is there negative feedback? Is there a path from the output to the inverting input? Yes, there is negative feedback. Therefore, V1 equals V2. Well, V1 is the input voltage, and V2 is the output voltage. So that means the output equals the input, which gives a voltage gain of 1. Pretty boring. Does serve a purpose. Okay. It's called a voltage follower. Now, the advantage of this, first off, because the voltage gain is 1, gives me the maximum bandwidth, right? Maximum bandwidth here. Voltage gain is 1, it means this thing will amplify all the way up to the unity gain frequency. Now, the other thing is the input impedance. No resistor. Very, very high resistance of this device. So I'm just going to, for now, we'll look at this a little bit more later. But very high input impedance. So whatever I hook this up to is really not going to draw any significant amount of current. If I hook this up to, say, a voltage divider, there's no load on that voltage divider. I don't alter the value. But I can use whatever that voltage coming in is going to be that voltage coming out. Now, because the op amp is being powered, it can drive current. I can draw several milliamps out of here to drive whatever I need to drive without loading the voltage divider. Very useful for that kind of purpose to go into other circuits. Think of it as a buffer, another way to look at it. Questions? So the last part of this chapter is just that big graph that I showed you with all the different op amps and everything else. So,
You need something different. You're supplying a video signal than if you were doing audio signals.
video signals are typically much higher frequency. usually in the megahertz. Whereas audio, of course, is a few kilohertz. Well, some of it's limited to a few kilohertz, but officially it's up to 20 kilohertz. Not that I can hear that high anymore.
Those are not considered objects then. According to this,
Yeah, they may not be.
the linear IC. Same thing with voltage regulator.
Yeah, voltage regulators are another form of linear op amp. Any linear op amp is anything that's going to utilize, or not op amp, but linear circuit, is going to operate in, what we used to call the active range, but basically had a proportional input and output regulated in some way for like a voltage rate. All right, I got homework for you. Now the homework, of course, is not due until 3 weeks from now. What is 3 weeks from now? That would be the 19th of March. Okay. Because we've got next week, of course, test number 1, and we got spring break, then we come back. Okay. So out of chapter 16, 2, 4, 6, 8, 10, 12, and 13. Lab, got experiment 41 and 42. Both of these are basically going to explore some of those characteristics of the op amp. They'll try and measure, like, for example, the input currents, and then see how much different they are. One things like that. So for 41, you'll do steps 1 through 24. I know that sounds like a lot, but not that bad. Okay. And you'll only do 2 op amps. I think the lab says 3. Just do 2. Just so you have a comparison. And you'll answer questions 1 through 9. For experiment 42, this is where you actually build an amplifier or two. Inverting amplifier, non-inverting amplifier. See those characteristics. So that'll be steps 1 through 25. But only do 1 op amp. I think it asks you to do 2, maybe 3, but 1 op amp is good because you're not going to see any difference. Right? That's the beauty of using resistors. You get very consistent results. Op amp almost doesn't matter. But for the characteristics in experiment 41, there will be some variability. And then you'll answer questions 1 through 6. All right, next week, of course, test number 1, which will cover everything we've done up through last week. That's chapters 11, 12, 14, and 15. JFETs, MOSFETs, frequency concerns, right? Upper lower cutoff frequency, calculations, decimal of this, decimal above reference, all that. As well as an amplifier circuit and cutoff frequency. So make sure you got all that down, right? Take home quiz.
Is that gonna be minus mirror,
What's that?
current mirror? Or are you gonna have current?
No, no current mirror. That's the only thing I didn't cover in chapter 15. Chapter 15, of course, differential amplifiers, DC analysis, AC analysis. Okay, you're quiz 3. Right? So quiz 3, take home quiz, quiz 2, quiz 1. There you go. With a few other things to come. And all the homework. There is no lab portion on the test. You can cheer later. All right, questions. Now, I do still have a few outstanding take-home quizzes. I'll have to look to see who. I don't remember who. I handed back the paper ones that I had, and I think I graded online. Did I grade online the ones?
Yeah, I know you graded mine.
Okay, all right. Well, make sure you get that to me. Good for you. All right. Rest of the time is yours to work on that.